morning, everyone. We are very happy to have Peter Anderson give a talk today. Let me introduce him first. Peter Anderson is a research scientist at Georgia Tech now. He obtained his PhD at Australia National University last year. As we know, he is an expert in the vision and language, and he has done a very wonderful research at intersection of the two areas. His research is focused on the image captioning and vision language navigation and VQA. He published many papers in the vision and language conference, such as CVP and NLP conferences like the NACO and SAL and Europe. Okay, welcome, Peter.
Thank you very much. Thank you. It's really exciting to be here, and I'm very much looking forward to the talk and hopefully questions and more interaction through the day. So thank you. So what I'm going to talk about today, I've called it Both Sides Now, generating and understanding visually grounded language. So a part of the talk will be about generating visually grounded language, and a part will be about the sort of other side, or the understanding side. And so I've kind of just picking on two particular things where we're working at the moment that I found to be very interesting. But in terms of the kind of overall motivation for this type of work, and I guess what some of my research interests are, the goal for me is building AI systems that have this sort of conversational dialogue or natural language interface, which really is the most natural way to sort of communicate with any system, but also systems that understand visual context. And I think this is a sort of very important piece that can go along with that, which can really find a huge number of applications with in terms of computing devices that can benefit enormously from some understanding of the situated or the visual context in which they're operating. So as an example, we're all familiar with personal voice assistants. One thing that we might consider asking these types of systems is something like, show me all the pictures of Ross from Stephanie's birthday party. And you might think there's quite a lot of sort of visual context understanding that would be necessary to answer this query. For example, there might be some images in a photo gallery with a cake, and then you might need to reason that some of these other photos were taken in that same location, and therefore they were also taken at the birthday, and then of course figuring out who Ross is in those pictures. But even in terms of things that we do in our homes and a lot of activities where we might want to use these voice assistants, we might be cooking and what's next? Okay, so now that you've chopped whatever that green thing is, now you're going to chop the basil and the oranges. And so visual context can be tremendously important to sort of getting value out of these systems. Another example which I think is very important is the sort of application, which is something I know that Microsoft has a great interest in providing tools that can aid people with visual impairments. So this is from a data set called VisWiz, and we have questions like, what color is this? And the answer is green. But also more difficult things, which might involve reading text, etc. Like, can you please tell me what this item is? It's butternut squash and red pepper soup. And just, I guess, one final example, not to sort of labour the point too much, but this sort of research interest isn't just applicable to consumer type items and consumer situations. I think there's a huge number of commercial and technical applications for this type of technology as well. So you might consider how you would normally interact with an inventory system or a kind of manual or set of specifications. Suppose in this case, the technician wants to ask what's the recommended spark plug gap for this model. it's obviously hugely beneficial if this type of assistant has some visual context. It shouldn't need to be told what this vehicle is. It's sitting right there. It's a 2017 Audi A4 and it has some particular type of spark plug gap. And then if there's a follow-up question of, do we have the new front bumper, then it's obviously important to realise that this is a metallic silver car and the bumper should be metallic silver, and we don't have that in stock. So my point is just to kind of demonstrate, I guess, that combining the sort of conversational aspect with the visual context is hugely beneficial once we sort of start adding this to our computing devices. Okay, so in terms of the outline of what I will talk about today, there's really the first part will be in terms of generating visually grounded language, and so I'll talk about the task of image captioning, but also a new direction. We're sort of pushing this task, and I guess we're hoping to somewhat lead the community, if possible, into an area where we can pursue the next set of research questions. And then in the second part, I'll talk about understanding visually grounded language by focusing on the task of vision and language navigation in an embodied, reconstructed 3D environment. So image captioning is something that people in this room are probably very, very familiar with. But to me, it's a very fundamental ability that we want these systems to have, and that is the ability to describe what they see. So given input such as these two images here, the desired output might be something like these captions: a man and a woman are riding an elephant along in a river, or something quite different: there's a large portion of pie on a platter. And one thing that I'll just sort of briefly mention when we're going to look at the performance of these models is that in terms of evaluation, if we have some candidate caption for an image, such as this one, a teal-green car with yellow and red flames painted on the front, the way that we typically evaluate these systems is by comparing a candidate caption to a set of reference captions written by humans, as shown here. Most of the evaluation metrics will compute the n-grams from both the candidate and reference captions and perform some sort of n-gram similarity score to then benchmark how similar that candidate is to the references, such as cider, blue, or meteor, or rouge. There's one alternative to this is some work that we did on the SPICE metric, where we first translate these captions by parsing them into scene graphs, and then we do a comparison in terms of the scene graph similarity between these two representations. And so collectively, these sort of make up the evaluation metrics for the official COCO leaderboard. And so if we look at any one of these metrics over time, in this case cider, we can see there's been huge amounts of progress on this task of image captioning. One thing that perhaps might make us slightly uncomfortable is that the human score is down here on the cider metric, and so it's not immediately clear what this gap here will represent and whether we are still making progress against the kind of stated objectives, I guess, of the research problem.
Can I ask you a question about the
Please.
data? So there are long periods of time where it's very flat. Is that just that the score of the leader on the leaderboard doesn't change, or?
Yes. So here
Are there really big gaps, like just before June?
So, yeah, actually, I noticed that as well. I did look back to see, was there a particular method that caused that? It actually wasn't so clear. Sometimes what happened, probably half of this or a third of this improvement is due to better CNN, residual nets and things, which then get bolted on the front and the whole level jumps up. So not all of this improvement is actually due to something to do with vision and language. It might just be, CNNs, etc. So, yeah, but given, I guess, that these metrics are sort of so much higher than human, it's sort of really worth digging in a little bit more to understand what's going on. So as a test case, I'm going to look at the work that I did here in my internship at Microsoft with Lei and others. So we proposed this model which we'll kind of use as an example. It's no longer state of the art, but it's close enough to be a sort of representation of existing models. The main focus in this work was an idea that we wanted to not just attend to the sort of spatial output of a CNN, but that we actually wanted to detect all the objects in a scene as shown on the right-hand side, and then we would, in the attention part of the model, cluster all the attributes of these objects together and tend to objects in what's effectively a sort of more human-like way. And so this has become the sort of standard approach now to image captioning and also visual question answering, or VQA. So we can sort of use this as a representative model. And so if we look at some of the outputs, here we have an image, and the generated caption from this model says there's 2 hot dogs on a tray with a drink, and this looks fantastic. And so we can look at a few more, 2 elephants and a baby elephant walking together, a brown sheep standing in a field of grass. So it's certainly the case that these types of models can produce some very, very nice results. One more, a man in a white shirt is playing baseball. So now we've hit a snag. Clearly this is not a person playing baseball. This looks more like some flying karate kick. If we look at another example, a zebra is laying down in the grass. Well, it does have stripes, but one thing about these models that is sort of starting to be better recognized is that they can be very badly wrong. And if we are really intending to sort of roll these systems out in things like aids for people with visual impairments, this could be a very costly mistake to make, mistaking a zebra for a tiger, or a tiger for a zebra. So it's sort of worth digging a little bit more here to understand what's going wrong. And if we look at how many mentions of these words occur in the training data, it becomes fairly clear what the problem is. So for a hot dog, there's something like 2,000 captions that mention a hot dog, and I think if you took all the linguistic variations, it's probably much more. There's thousands of elephants in the COCO data set, which is the training data here. There's lots of mentions of baseball, but actually only 5 captions in the entire COCO training set that mention karate at all. So we assume the model sort of learned nothing about karate. Sheep are sort of everywhere, and again, I was actually surprised that COCO even had 105 mentions of the word tiger, but not all of them are actually referencing the actual animal tiger. There's all sorts of tiger motifs and other things. So effectively, the tiger is non-existent in the data set as well. So our problem here is that the COCO data set, which has been formative in driving this entire area, has this characteristic that although there's almost 600,000 training captions, there's 5 captions per image, so there's about 120,000 images in the training set. But this was collected on the basis of 91 original objects, because it was, as people in the room would well know, primarily an object detection data set with image captions added as well. And so there's very, very dense coverage in the data set of these 91 objects. You can pick out the things we're talking about. They're all here in that set of icons. But for everything else that's a visual concept that we would be interested in, it's not represented here, or certainly not represented well enough that we can learn it. And so the big question, which to me is the next sort of major research question, is how do we go from models that do well on COCO in this data set with this very narrow set of visual concepts and very deep training data on those concepts to something that we can actually deploy in the world, where we have a very long tail of visual concepts and not so many clear ideas on how we're going to learn them. So of course there is one idea, which is that we could simply collect more data. And so we could go and pay people to write captions for these particular images, and we might get a man in a white shirt is doing a karate kick, or a tiger is laying down in the grass. But it should also be obvious that there's a lot of redundancy and sort of duplicated effort here. The model should already know about men in white shirts. It just didn't really know much about karate kicks. The model knows that animals lie down in the grass. You know, this is sort of represented in Coco, but the key here is that this is a new animal, the tiger. And of course, there's also the argument that, you know, trying to collect captions for all the visual concepts in the world is just going actually to be completely prohibitive. So there are alternatives which people have started to examine. And so one alternative, if you sort of take the idea that mostly what we're missing is understanding of the objects and the kind of nouns, and that, you know, understanding sentence structures and adjectives and things are reasonably well covered in things like Coco, then we should leverage object detection data sets in order to provide annotations of the missing grounded nouns, and we can build models that can then assimilate that information into a captioning model. And one nice aspect of this idea is that these data sets are orders of magnitude larger than Coco. So, for example, the Open Images data set has something like 9 million images, 600 object categories. And also, there are methods that people are developing to kind of collect these data sets more or less semi-automatically at very, very low cost. And so this would offer a way to kind of scale up to, you know, in the end, trying to build models that can have an impact in the world by leveraging this type of data. And then on the sort of NLP side, there's been huge interest recently in developing stronger and stronger language models from unaligned text corpora. You know, and we would have to believe that things like Wikipedia and other text corpora can have an impact here in terms of scaling up as well. And there may well be lots of other things that we haven't yet considered.
Sorry.
Yes?
Can you elaborate more on the second one, how the text corpora can help the object detection or the caption?
So if you consider one of the examples we'll look at is, for example, you want to be able to understand and describe sea creatures like dolphins or whales or jellyfish, and there's nothing at all in Coco that's sort of remotely similar to these sea creatures. So in order to understand how we can talk about them, what types of activities they might do, like swimming, for example, you could conceivably learn that from things like Wikipedia or really any text that's describing a jellyfish or a dolphin swimming, because we can't learn that from Coco if it doesn't include any animals of a similar class that we could sort of extrapolate from.
Okay, so you mean that you still assume that the vision can do the object detection, but the actions the objects perform can learn from kind of text corporas.
Yeah, so I guess in language terms, you know, the verbs and adjectives and pronouns and sort of all of this stuff we need to know as well in order to describe these things well. And all of that can come from the language side.
So that part is mainly just for language model, right? It's not the language image mapping.
Right. So in the kind of models that I'll show at the moment, we're using pre-trained language models like Elmo, but you know, this may just be the first step towards something that is more inclusive of both.
So this looks like a zero-shot learning in computer vision.
Yeah.
Right? So the idea is to leverage language prior to learn something in visual
So
space.
sometimes the language apply can be helpful.
Yeah.
So the zero-shot reference is good, actually. We did talk about this type of work as a zero-shot task in one paper, but reviewers didn't like that because it's not clear exactly where the boundaries of the sort of zero-shot task were. So
not a trivial problem.
yeah, so we stopped calling it zero-shot, but it's definitely a link. So having sort of built up this huge motivation, let me now introduce this data set, or actually we're calling it a benchmark because in line with the overall aim here, we didn't collect any more training data. We're simply providing validation and test sets in order to test models that are going to exploit data that already exists. So the training data looks like this. So we have the COCO Captions training set, which contains, as you can see at the top left, images and captions associated with them, covering about 80 classes. So originally it was collected for 91 classes, but around 80 of them are actually then maintained in the data set. On top of that, what we're going to add to the training set is the Open Images object detection data set, which covers around 600 object classes and about 1.9 million images that have these bounding box annotations of those 600 classes. So this covers a much, much broader set of visual concepts, things like artichokes and accordions and dolphins and all sorts of things that are not found in COCO. And our task will be to then generate captions for the Open Images validation and test set. And so we can then break that down into sort of 3 categories. The top one is what we're going to consider in-domain images, and these are images that just contain objects, classes from the COCO dataset, and any existing model should do sort of reasonably well on this set. The second is the near-domain set, which contains a mixture of classes from both COCO and Open Images. And then the most difficult part of this will be captioning images like this, which contain only what we call the novel classes, the classes for which we have no training data containing an image and a caption for that class. And so this task has been sort of popped up previously in the literature as a task called novel object captioning. So NOCAPS is a kind of a short for novel object captioning at scale. The prior work here has really begun from a CVPR 2016 paper from Lisa Hendricks, which was called Deep Compositional Captioning, that sort of posed this problem. And then there's been a number of follow-up papers from there. But the main thing, I guess, that we're wanting to do to sort of extend this work is to move from the previous evaluation scenario, which was on a held-out version of COCO, where we simply held out the training captions for 8 object classes, to now scale this up to something that's much more meaningful. We've sort of had this proof of concept data set with 8 novel classes, and all of those were similar to some class that had captions. So, for example, in the original setting, horses were a known class and zebras were a novel class, and it was reasonably easy to, if you could talk about horses, then you could also talk about zebras. So in the new version, I guess these differences can be much larger. And also the evaluation setting, yes?
So does this assume that all the actions and relations that you'll see in the Open Images are covered by COCO?
Right, so I remember now I meant to repeat the question. So the question was, does this assume that all the actions and relations are covered by COCO that you will need? I think the answer there is sort of. So when we analysed the data that we collected for the validation and test set, the captions, we found that many object classes were new, but most of the adjectives and verbs were already found in COCO. So it seemed like getting the kind of nouns or the object classes right is the major part of the problem. But having said that, there will be some adjectives and attributes and things which are not covered in COCO. And as this task develops, we should be looking to use language models and other kind of text corpora to try to fill those gaps. So we don't explicitly assume that we should be able to do everything from COCO and Open Images. We're sort of very open to posing this as a task where we want to find other data sources, particularly text corpora, that can help as well. Okay, so I guess in terms of what's the sort of learning problem here, this does include aspects of both domain adaptation, because there are some relatively small differences, for example, in the types of images in Open Images versus COCO, not only from the fact that there's new classes, but there are differences in the way some of them are composed. But then there's this transfer learning element where we're really wanting to get value out of an object detection data set. Just so to briefly explain the data that we collected to cover this benchmark. So we selected 4,500 validation images out of the 42,000 in open images, and about 10,000 of the test images to constitute the NOCAPS benchmark. And this was done in a way to sort of prioritise an even distribution across classes and to select relatively more complex images that had multiple instances of different objects featuring together. So the full details are in the paper. But what we end up with is around 4 object classes in each image, which is a little bit more complex than COCO, and around 8 object instances per image, which again is similar to COCO. The collection interface.
How is the
Yes.
difference between classes and objects?
So we're talking about object classes being 4, object instances being 8. So you might have 2 dogs, which would be 1 class but 2 instances. Yep.
And those could be 2 kinds of dogs. They could be.
Yeah. So this is with respect to the kind of class definition from Open Images, which is dog rather than what type of dog. Yeah. So in terms of the collection interface to collect this, it's very similar to COCO. One thing that we sort of would point out, which we discovered as we're trying to drive into many more visual concepts, as we find in this Open Images, is that sometimes workers didn't actually know what these classes were. And so we ended up deciding to prime them with a set of keywords that contained the ground truth list of object classes in that image. So not such a problem for this example, but in cases like this image, yes?
I just got a question about when you're gathering the data labels on Turk. Can you talk some about the different quality problems you encounter? Because, for example, we're doing a very similar labeling task on Turk right now, and we've discovered a huge increase in the number of what appear to be bots on Turk that are trying to take the tasks and trying to generate labels, and it's become really difficult to weed those out. I was wondering if you've encountered this.
So the question was about the difficulty of collecting this type of data on Mechanical Turk and a rise in bots that are exploiting these tasks. So the way we set this up, I'll preempt a little bit where I'm going to go. We ended up collecting 10 captions per image. The reason being that this made our evaluation metrics like SPICE and CIDR more effective. And when we were collecting 10 captions per image, we then, in the process, would compare the CIDR score between each of those captions with the other 9, which was a way of kind of flagging suspect captions. So we could then automatically flag them, and we have enough grad students running around who could then check them. And so then if we find a worker who's producing low quality, we can sort of get onto that fairly quickly and block them. So that's the kind of basic setup, I guess, we use for quality control, and that seemed to work fine. Yes?
For the keywords, you use the ground truth keyword in the open image dataset?
Yes.
So if the image has a lot of ground truth classes, you will do some selection, or you will just output and give all the labeled classes keywords?
So the question was, do we show all of the Open Images classes if there's a lot?
Yeah.
So we excluded the classes that are considered as parts. So there are classes for human eye and human nose and registration plate of a car, and basically these are categorized as part of some other classes. So we excluded those, but we included everything else. And so the impact is something like this as an example. This animal on the left is actually a red panda. Many people wouldn't know that. They don't recognise kangaroos either. I should have used that as an example. But so without the priming, we get a brown rodent climbing a tree. But when we provide this priming, then we get higher quality captions. So one thing we're concerned about, I guess, is that this reduces linguistic variation. We did have a look at the number of unique n-grams compared to COCO in an equal-sized sample of the data. And as you'd expect, it should be more because we have more objects, and it is more both in terms of the sort of 1 grams, but also 3 and 4 grams. So, we're sort of reasonably happy that we still have quite a lot of linguistic variation here.
So are the workers told to use all keywords, or is that what?
So the question was, should they use all the keywords? Good question. We did say in the instructions, somewhere here, it's not mandatory to mention any of the keywords. So that it was really hoped that if they were trying to figure out what some object was, they could look at it, but apart from that, it wouldn't sort of impact their caption too much.
Question though, how does the keywords change your ability to filter out the spam and bots? Because presumably I would write a bot for this task that just used all the keywords, and then the CIDR measures and things would actually probably work out pretty well for me.
True.
Is that an issue?
So we didn't think too much about that problem of could you write a bot that would regurgitate the keywords. If you put your favorite image captioning model in here, you probably would have snuck through our system reasonably well. I'm not sure if any of the AMT workers are doing that, but I guess that's the next line of defense against these, this type of exploitation. It's probably something we'll need to think about in future. Okay, so I mentioned briefly before that we actually collected 10 image captions for every image. So the reason for that, in both our prior work and other prior work in the CIDR metric, people actually looked at how many captions you need in order to get a high correlation between the metric that you're using and the human evaluation. And so it actually looks like the sweet spot for this is really around 10 reference captions, as you can see in these plots which we've lifted from these two papers. And so that's what we did. And so what we end up collecting is 166,000 captions, which is 10 for every validation and test image, and 1 more to serve as a human baseline.
What's the difference between the human baseline caption and the others? Or are they just all collected in the same way and you pulled one out?
They're all collected in the same way, and then we randomly sample one. And then, so the purpose there is just to basically find a human performance level for the task. And that human performance level is helped a little bit because the humans got the keywords as shown here. And so we're not giving those ground truth keywords or object classes to our models, but that's fine. We're sort of, we're happy to help the humans out. So just to provide some sort of example of what this actually looks like. So here is an image from the in-domain or the near-domain category, which has a man there, which is obviously something well understood in COCO, but a camel, which is a new class. And if you look through, a very long list of captions, but it is sort of clear that if you collect 10, you really do capture all of the kind of linguistic variation that's likely to occur in a well-formed caption. And then here's just another example. So we're getting a much wider variety of visual concepts, I guess, things like this tank or this military vehicle. There's a lot of things in open images that really are quite different to COCO and are therefore quite challenging to train a language model or a captioning model on COCO and then extrapolate to these images as well. So, right, now let's get on to the models. So the first baseline model that we're going to use is the one I mentioned before, which is our bottom-up and top-down attention image captioning model. And so as a kind of baseline level of performance, we just train this only on COCO, and then we'll look at what happens on the NoCaps benchmark. The second approach we're going to look at is something that we worked on a little while back in terms of how you might approach this task, and the idea was that we would add constraints at test time to somehow force the model to just generate the word that we have detected from an object detector. And so here, for example, we have an object detector that might detect the words tiger and grass. What we did was that we encode these two visual concepts in a finite state machine that will just only accept strings that mention these two words, and in doing so we can account for plurals and we can account for synonyms and build all of that in the finite state machine. So for example, as long as, in this case, if the caption included the words tiger or tigers, that would be fine, or grass or vegetation would be synonyms, and either of those would be fine. So having detected some visual concepts with an object detector, encoded those in a finite state machine that accepts strings that satisfy, we then use constrained beam search in the decoding to find, so in the case of beam search, it's the usual approach to find high probability output sequences. So here what constrained beam search does is find high probability sequences that also satisfy that finite state machine in terms of hard constraints. So that finite state machine is then an additional input, and then rather than getting something like a zebra laying down in the grass, we'll now get a tiger is laying down in the grass. One detail here is that you do need to have some sort of word embedding that can cover the new vocabulary, and so as we'll get to in the results, we use the forward direction pass of the Elmo language model to provide those word embeddings during decoding, and the model is trained at training time with those embeddings as well. And so there's a lot more details in the original paper about setting this up. The other model that we consider, because we want to sort of capture, I guess, different ways of approaching a task like this, this is a paper called Neural Baby Talk, which was from Georgia Tech in CVPR last year. And the idea here, the Baby Talk paper was a paper that generated templates and then filled the slots with visual detections. So this is the neuralized version where the template is generated from a captioning model with an LSTM output. So you can see here, this is the sort of template that might be generated where the slots are grounded in the image, and then those slots are filled using an object detector as well as some additional machinery to try to sort of figure out, are we looking at plural or singular, or what fine-grained class is this out of a larger selection. And so the nice thing about this Neural Baby Talk model, it provides a concrete visual grounding of the things that you're generating. And so because of that, you can swap out the object detector for one that's trained on open images, and now you can go and caption, hopefully caption a lot more of these new classes that you haven't actually seen training captions for. Okay, so the use of an explicit object detector here makes this sort of applicable to this new NoCaps task. Okay, now let's have a look at the results. There's a huge lot of numbers up there, so I'm going to try to pull out a couple of trends. First of all, how hard is this task? So the top line there shows the performance of the baseline model. So in terms of, say, slider, it's about 56 overall. Once we throw our full model with all our bells and whistles, so we're using Elmo, plus we're using constrained beam search. I'm sorry, I've actually highlighted the wrong thing. It should be the line above. So row 3, so the CIDR score increases about 20 points to 74, and then the human score is about 87. So we've got something like halfway between the sort of baseline model and what humans are doing. So this is kind of nice because I think we mentioned earlier on that on the COCO data set, we're so far beyond human performance now, we're not sure if that's actually meaningful. So here we're still well under human performance, which hopefully can give us some more confidence that pushing in this direction means something meaningful. The second thing worth pointing out is that incorporating the language model like Elmo does help, but not as much as we might have thought, and most of that improvement happens on the out-of-domain subset. So that's this sort of number here going from 66 to 71. And so quite surprisingly, even on the near-domain subset, there are classes like the tiger, which, although they're not part of COCO, they do appear a couple of hundred times. And actually, the models can still learn a reasonable word embedding for those classes, even from COCO. Whereas it's really only the very distant classes, like the dolphins and things, that benefit from having Elmo as a language model most of all. Yes?
Do you think that constrained beam search is actually shadowing or like if you weren't using that with Elmo perform better? Like you would see more improvement compared to the baseline?
So we do have numbers for that, not in this table, and it actually was about the same.
Okay.
Yeah. So
Same as adding the constraint?
no. So when I mean about the same, not much better than the baseline. So it was a little bit better. We also we looked at using glove embeddings. There's also a dependency embedding that we've used as well that's useful. These things help a little bit, but on their own are not enough to sort of because I guess the model still hasn't been trained to actually generate any of these new words like the tiger, or at least very lightly trained. And so you do need a way to kind of encourage the model more strongly to produce those words. I'm sort of focusing mostly here on the constrained beam search model. With Neural Baby Talk, the results are similar, although not quite as strong overall. Probably the final thing, just in terms of results I want to pull out here, is that better object detectors help, which is something that we should hope to find. And so when we can give these models the ground truth object detections, and the performance increase is fairly significant, another 10 CIDR points or so. And so we can get some tailwind here as people build better object detectors, which will obviously go some way towards helping with this task. But even then, it's worth noting that even with the ground truth detections, these models are not as good as human. So there's still a lot more that is not just a problem of recognizing the object, but the more complex problems of understanding the visual saliency of that object, of the types of verb and adjective relations that it might sort of be experienced with, and all the rest.
Be very careful along those lines. If you're comparing to human, it's interesting to understand the variability across humans and what they generate, and then secondly, the kinds of differences that are still there between humans and the automatic systems.
Yeah.
Do those fall into a small number of classes?
The second part of that was the types of...
How much variability is across humans?
Yeah.
And then the second is, in what way do humans differ from the models? Is it recognizing dolphins? Is it being able to talk about what the dolphins are doing?
Sure.
Is it nouns, verbs, adjectives?
So the first question, I guess, is what's the sort of interhuman agreement? So in some ways, the human score at the bottom is a measure of interhuman agreement in that we're comparing one human caption against 10 others. And so we also compared that against COCO using 5 captions, so that it will be like for like. And the human agreement across this data set is very similar to the human agreement in COCO, and it's sort of, I guess, characterized by these scores in that humans agree with each other still significantly more than our models agree with humans.
To be fair, you've given the humans very specific instructions on how to caption, right? Like you told them, you have to use 8 words and don't use this word in one sentence. And if you just asked humans in the wild without constraints to describe an image, you'd see a lot more variability in how they do it.
And even in your red panda example, one image was lying in the grass, another was climbing a tree. There was a fair amount of variability in what was happening.
So trying to understand where the models are falling down relative to human is sort of difficult to, I guess, characterize in some ways. I'll show a few examples that might sort of help. So here's some examples. So we've got the human caption at the bottom. At the top is the baseline trained on COCO, and then we've got a couple of the stronger models in the middle. And so there's a few things that go wrong. A baseball rifle. So we've got a baseball player holding a baseball rifle in a field. So sometimes there's a sort of inherent problem about the grounding here, in that if this model is sort of grounding this as a baseball rifle, then, or perhaps this is even a better example, a marine mammal sitting on a dolphin in the ocean. So the model's sort of failing to realize that this marine mammal and this dolphin are actually both grounded on the same thing, and therefore I don't need to mention this twice. So in COCO, a lot of issues of sort of visual saliency, of picking the right entry-level class. Is this a dolphin or is it a mammal or an animal? All of that stuff in sort of COCO is somewhat expected to be learned from data, and we don't need any explicit models for that. Whereas in this type of task, it comes much more to the focus that we may need to explicitly model the grounding so that we don't ground the same word twice in the same place, or the saliency of various things in the image so that we know which of our detections we need to mention. And so, yeah, I think, I guess these are a few examples of the way things go wrong, and it then leads us to a few directions that we can sort of move to help.
So if you perform the object detection, you would have the bounding box information for example, for both mammal and the dolphin. So in that
Yes.
case, will that information help you to avoid this kind of caption result?
Yeah, so the comment there is that using the bounding box information, you can avoid this sort of dual grounding problem, and I think that's a nice idea as a way to kind of further develop, which we're not doing at the moment. So at least not in the up-down model, because it's doing the soft attention, but there's no limitation there from the stop it grounding multiple words in the same spot.
For this example, the issue mainly comes from your algorithm treats them as two individual objects. Right?
Yeah.
So actually, they are the same thing. Right?
Yeah. So I'm actually probably running a bit slow, and I do want to talk about some other stuff as well. So maybe I'll move on to the second part of the talk. So to sort of sum up, I guess, what we're proposing here with this NoCAPS benchmark, we do think that when COCO was developed, the question was, can we even attempt image captioning? Our question now should be, at least in our view, can we make this work in the real world on arbitrary images? In order to do that, there seems to be a strong argument that we want to transfer knowledge from a variety of different data sets. And so we've proposed this NoCAPS benchmark as a way of tracking our progress in trying to do that. And we've shown that things like better object detectors and better language models can help. But I think there's also a bunch of sort of other explicit challenges that are more obvious in this data set than COCO about determining which objects are salient, what should be the entry-level noun that are used to describe a category, ensuring that we don't ground multiple objects to the same place, etc. So that's the NoCAPS benchmark. And by the way, so this is all available, the papers at this website. The test server and the actual data will be released, I would say, in the next week, most likely. Yes?
Just a small question. So, especially now you're like focusing on out of domain, in the wild scenarios. Do you think it is possible to even have a system? It's a much humbler task, which is just outputs. I am not confident that I should be making a prediction on this image, right? Like that this is out of domain for me.
Yeah.
Both maybe from the language and vision side.
I believe Microsoft has that. So the question was, can you build a model that says I'm not confident about an image? So I believe you do that.
We do have an algorithm to reject for the captioning result when we are not very confident.
Yeah. So I should mention here, we're kind of pushing this as moving to captioning in the wild. Microsoft is actually doing that in terms of rolling this out, but the difficulty is that 20-30%, which is the I don't know, and so that's really what we're pointing to here, is how do we fill that gap, which is currently the I don't know. What is it, 20 or 30%? Or?
I don't remember the number. Xiaodong did that work before. Yeah.
Okay. So I might just speed up a little bit let's move on to the second part. So here, the other side of the coin is understanding or comprehending this visually grounded language, and the task that I'd like to talk about here is an instruction following navigation task, which we've called vision and language navigation. And so you may wonder, I guess, why we should think about an instruction following navigation task for visual grounding and comprehension when there's so many other things like referring expressions and things. I do believe that we're sort of in this interesting stage where we're moving from static images to environments that we can use for learning and training. And there's something important that sort of happened, which is that 3D reconstruction got to the point where it started to work well enough that you could give these systems to non-expert users who could create good quality 3D reconstructions. So an example here is this Matterport camera. And so now there are these very large data sets, and even this one company, Matterport, has something like 1 million house and building reconstructions. And so in my view, ImageNet was very transformational for computer vision. ImageNet could not happen until you first had Flickr. You first needed crowdsourced images at large scale, which you could then annotate and build data sets on. So this is the sort of next Flickr, having these large-scale 3D reconstructions that we can then annotate and learn on top of, to me at least, opens up a high, huge range of sort of opportunities in that area. So, and not just to me. There's this sort of developing stack, I guess, where we have this sort of raw data. We then build environments on top of it, and we propose tasks and metrics and algorithms. And there's been a lot of recent work in this space. Matterport data set, Stanford, there's another Gibson data set since then different types of environments with different characteristics on top of these, and then different tasks and things. So our primary interest here is in the sort of, or at least mine is in the sort of vision and language space, where a lot of these are also just in terms of, can a robot navigate to a point, etc. So, and it's interesting that I guess all the work here has been in the last really, well, since 2017, and there is more that's not featured. So in terms of recapping the work that we did in this area, so we proposed a simulator for embodied visual agents based on this data set called the Matterport 3D dataset that has about 11,000 panoramic RGB images, also with depth, that look something like this. It covers around 90 buildings. Often they're very large, and there's a bunch of other useful data in there, annotations and 3D reconstructed meshes, etc. What we did was we built a navigation graph over these panoramas, and we constructed a simulator that basically allows an agent to move between these panoramas, look around in any direction, and then sort of jump to navigable nearby locations. So at any of these points, there's a 3D panorama, and then trajectories will be paths throughout this graph. And so this particular trade-off is because we wanted to maintain, really high quality visual information, and we didn't care so much about having continuous motion in space. So we proposed this vision and language navigation task as an example, something like this. Beginning at a position in this reconstructed building, given a natural language navigation instruction, can you find the goal location? We sampled around 7,000 of these paths and collected 3 instructions for each using Amazon Mechanical Turk to create the room-to-room data set. And so this is a data set where the instructions are on average about 29 words. The trajectories are on average about 10 meters. But given the vertex degree in this graph is about 4, and so over about 6 steps, there's actually a large number of places you can end up. So this is quite a challenging task. So to give some example of what this looks like in situ, here's an agent navigating from this instruction. And so there's sort of jumping between these panoramas or turning. And in this case, they went too far, but I think they're going to go back and get somewhere close to that couch, which was actually the intended target. And these are sort of interesting environments because they're human environments. There's an awful lot of reflections and glass and things that make this quite challenging to do 3D reconstruction, which is another reason why we prefer to use the original panoramas rather than the 3D mesh as the kind of agent's perception. So we've been very happy that this has attracted quite a bit of attention from the community, including folks from Microsoft, and there's been some really interesting work. So I think something like 28 submissions since September. And so in terms of what's been driving the progress on this, There's some interesting ideas that are being investigated. One thing is using models of both the speaker or the instruction generation as well as instruction following. And so doing sort of pragmatic reasoning. There's been a lot of work into better modelling of particular issues that come up in an environment like this, like when to stop, which is something that in many RL scenarios, the environment just stops you because you've arrived at the goal. But in these types of problems, you actually need to figure out when to stop. You might need to do reasoning about backtracking. And more recently, there's been some interesting ideas about how you do dropout in an environment. So there's this concept of environmental dropout in this NAACL paper where we just wipe out whole classes of objects from the environment to then synthetically, effectively generate new environments, and this will generalize more effectively. Yes?
So has most of the application of this data been for kind of agents and robots, or has there been anyone looking at how this kind of data would apply for supporting indoor navigation for people who are visually impaired? And what do you think needs to change about the data or the way it's presented to make it more useful for that scenario?
So that's an interesting question. The question is, to what extent is this useful for indoor navigation for people who are visually impaired? One aspect of this is that the instructions themselves have a lot of visually grounded content. Go through the kitchen, go past the stove, etc., which is what we wanted because we're interested in this visual grounding. It's not clear to me whether you would get that being provided to the system by a visually impaired user. So if it may be that you sort of have a higher level and less procedural instruction, and so this may not be the ideal data set for that. But the general idea of how you can collect and sort of work on this is probably still applicable. Okay, so in terms of, I guess, the limitations in current work, so one thing we're guilty of a little bit in the computer vision community is we throw a sort of end-to-end neural network at virtually anything. And in this approach, all of the reasoning here, all the models are working on the image space. And that makes it very difficult to reason about spatial relationships between things. And a lot of models are doing things like beam search in order to get the best results, which helps substantially. But you're effectively moving multiple robots through the environment and sort of teleporting them from place to place. And so it's not necessarily conducive with actual robotics, although it's sort of perfectly fine as a way of understanding more about the problem. So what we would like to do is, first of all, incorporate some more geometry. So we've extended the simulator recently to output the depth images as well to the agent. And we're constructing semantic spatial maps. And so what we're doing here is taking the input depth and RGB images, projecting, so running a CNN to get feature representations and projecting this with a pinhole camera model onto the ground plane. We use a convolutional GRU to then update that representation as the agent moves around. And we build a spatial semantic map of things that are in different locations. And our goal here is to then reason about all the different trajectories in that map rather than actually moving the agent around and doing these things that are not conducive to robotics. We can do all our trajectory reasoning in the map that we're building. And so this idea of this sort of spatial semantic map is popping up in a couple of places. There's some references at the bottom. So interactive question answering was one. There's a paper at CVPR last year called MapNet that used an idea like this for localization as well. The question that comes up is, if I gave you this map, and let's suppose we have the complete map at this point to understand the sort of, the ideas, how would we use it? And so here's an example I will pose to you, the audience. Here's your instruction. Here's a floor plan which you can take as a representation of the map that the robot may have built. And where do you think the goal is? I admit it's still...
I just have a question about the floor plan.
Yeah.
So wonder, to what extent is this representative of what's in the data set right now? Because it looks like, in real life, nobody's house is this uncluttered, for example, right? Like, there's no random objects really on the floor. And I'm wondering, is the data set all kind of like, you know, model homes that are unnaturally clean? And in that case, how realistic are the tasks that are being generated?
That's a good question. So the question is, you know, where is the clutter and is this a real house? So it is a characteristic of the Matterport data set that most of the people who've invested in these cameras and captured these homes are high-end real estate agents, hotels, museums, churches, researchers now. But there's not too many, you know, very messy, untidy homes that people are digitising. And so that is a bias in the data set. Nevertheless, it's what we have for now, I guess, but it is definitely a bias. So here, the starting point is this red location here. The instruction says turn and walk out of the bathroom into the hallway. Let me make it a little bit easier for you. Here I'm going to highlight some of the things we're looking for. We want a hallway, shelves and a sink, a kitchen area, a stove and a sink. It may still be hard to see these at that resolution. I'll point out to you that in this area here, this is a sink, a stove, a kitchen area, etc. So that'll probably give you some fairly strong clues. And then we can also look at the sort of action commands that are in here, the turn and walk, walk through, continue through, walk past. And so hopefully you can at least believe me if I tell you that the actual goal was down here. So we were going to walk past, so this was a bathroom, we go past this sink, walk through, past the sink and the stove, etc., and get to the goal. It would be easier to do in person than it is from this low resolution map. The point I want to make is that what an instruction is a sequence of observations and actions. And that's predominantly what we're sort of getting here. And so if you have a map and a sequence of observations and actions, to us at least, it starts looking like a sort of a tracking problem. Where what we want to track is not where our agent actually is, but where would we track the human demonstrator. If we had a set of instructions that we could encode into a latent set of vectors that would represent observations and actions, and then we have some representation of our belief of where the agent is, and we want to build a Bayes filter in order to figure out where that agent would end up. And so that's the kind of main idea here. And what I'll do is I think I'll wrap up because I'm going way too long, but I'll move quickly, but I'm very happy to talk about this in as much detail afterwards. Okay. Okay.
I think that's right?
Okay, as long as it's not, well, I guess anyone who needs to go will go. Okay, so I'll try to sort of explain what's going on here because I found this to be a really interesting idea. So recently there's been a couple of papers that have done sort of differentiable particle filters, differentiable histogram filters, and shown that you can take this Bayes filter idea and encode the whole thing in a neural network and make the whole thing end-to-end differentiable. And so we're leveraging that work. We're representing our belief over where the agent is with some sort of histogram spatial map. And then we're going to take our instruction, decode it with a sequence-to-sequence model into two sets of latent observations, which we'll use one as a motion model and another to drive an observation model to update our belief. And so the motion model will update our belief based on where we think the agent can move to, and then the observation model will provide a probability of observations given the state and the the probability of the observation given the state, which we will learn directly. In terms of how we implement this, the observation model is based on this model called LinguiNet that was proposed by a Cornell group that was working on instruction following in AirSim, actually. And so they proposed this. It's a sort of a UNet pixel-to-pixel architecture that takes language encoding as well and tries to just directly output globally where the goal is of some instruction. So here, we're not going to try to do this globally. We're going to be reasoning about the trajectory with our motion model, and so this will become a piece of the puzzle and not the whole thing. In terms of how the agent can move, it's a really neat idea, I think, in that if your belief is a histogram in a tensor, then you can update that with a motion model that's just a transposed convolution. Because what a transposed convolution will do will be to take your current belief and then distribute that into your updated belief in some sort of local neighbourhood. So it has this nice locality property that we want, that the agent can't just jump all over the place, they have to go somewhere that's nearby. And so the parameters of that convolution are actually generated by the sequence-to-sequence model from the instruction. So this whole thing we then train end-to-end by minimising the KL divergence between where the actual human demonstrator is and where the model belief is given the instruction. So that's the kind of idea here. Yes?
So in robotics, we always, whenever you have such high resolution maps,
Yeah.
even reasonable ones, and Visual SLAM is pretty good now, right?
Yeah.
There are products launched using the SLAM and whatnot.
Yeah.
So often I often think about is, if you have a map, right, why won't I just run? You don't even have to run SLAM, right? You can just run localization.
Yeah.
Right, and that will tell you exactly where you are in metric coordinates.
Yeah.
Sometimes even you can run topological SLAM, and then your job becomes so much easier, right? Because then your base filter can just be a classifier.
Yeah.
You don't need to do base filtering, right? So which has its pros and cons, but is often swept under the rug, right?
So I'm really glad that you've raised the issue of why not just run SLAM, and SLAM works well, and I totally agree. So one thing that I want to make sufficiently clear is that in this whole setup, we know where our agent is at all times. So we're almost assuming that someone's running SLAM, thank you roboticists, and that we can keep track of where we're going. Our problem is to work out where the goal is from some natural language instruction. And so what we're tracking here isn't where our actual robot is. We're tracking where the human demonstrator would go when they started from the start position and took that instruction.
See, that's your later space.
Yeah, so we've kind of, we're just borrowing the machinery in a sense to try to solve a slightly different type of task with it. And so this is going to be a component within our model, and then the whole story is that you then add a policy that takes this belief map that they can then learn. So at each time step when your robot moves, you rerun your filter to get an update of where you think the goal is. Then that feeds to a policy that can learn do I explore now, or do I try and exploit this? Am I sufficiently confident? So that's the kind of whole setup here. So let me try to show some examples. So what I'll show on the right is this filter running on the instruction that we looked at before. And so the green part is the sort of motion model update. So we've started at that red dot, and then the motion model has sort of said, right, we could end up sort of anywhere nearby. And actually this is even a fairly dumb version of this, because here the motion model, the belief doesn't even include the agent's heading. So that is actually going to be important, and we're incorporating that now. But here, the motion model just kind of spreads everywhere, and it's still a fairly primitive version of what this can be. But we then get a observation update. Sorry, the purple's a bit hard to see. But what this is showing is that this area here seems to be reasonably likely according to the observation model, and that's because it has all the sinks and stuff there that we're looking for. So then we complete our update, and this is our new belief, and we've kind of moved in the right direction for where the instruction should actually be taking us. We then take another prediction step with the motion model. We take another observation model update. We combine these to get our new belief, and so we're now sort of somewhere in this hallway. And so we carry on with motion updates, observation model, combined updates, and so we can kind of step through here. And if I stop without going over, we end up at the goal. And so you can kind of see how this belief is propagated. We're not just sort of globally trying to predict where's the goal, we're actually reasoning about all the trajectories that can get us there. And so, yes?
Just going to ask, have you tried injecting noise into the instructions, like maybe a wrong action or observation?
You mean in terms of like changing words in the instructions?
Yeah.
Yeah. So in order to
Just the robustness, because it seems like a robust.
yeah, so this is, I should, I guess, make very clear. Like this is a kind of work in progress that we're sort of currently working on. But I felt it was interesting enough and developed enough that I wanted to talk about. But we haven't. So yeah, we haven't sort of yet, tested this every different which way, and that would be, a nice thing, I guess, to do is to change the instructions and then see, can we, reliably steer this in different places? Does it make reasonable mistakes? And one of the points, I suppose, is that because this does give us quite a good insight into what is driving the model's behaviour, then hopefully it's reasonably interpretable what's going on, when it does make those mistakes. Yes.
So for this problem, do you just assume that the top-down view is available? Only the top-down view is available rather than the updated view whenever the agent is moving to a new location?
Yeah, so the question is this top-down view fully available? So in this scenario, what we had here was we had an agent walk around for a bunch of time steps and collect a map, and then we're just running this on that map.
Is this the only input to the algorithm, or the agent actually had the updated view?
So let me maybe try to answer that with a sort of fuller experiment. So what we did here was we took a bunch of fixed trajectories where we want to sort of go towards the goal, but not perfectly. Hopefully, similar to what the agent does with a policy attached. And so we 70% of the time take a step towards the goal, and the other 30% of the time we randomly go somewhere, and we end up with a trajectory. We run the mapper that builds the map from that trajectory, and then at every time step we run our filter. So the time steps 0 through to 5 are kind of increasing amounts of trajectory and map, and then we try to predict the goal location. And so you can see in the top row how many sort of meters squared of map area there is, so there's sort of more and more as the trajectories get longer. In the second row, it tells you whether you've actually seen the goal yet, because of course early on you won't even see it, it's typically around a corner. But by time step 5, 67% of the time you have actually observed the goal now. So it's challenging in that you're trying to predict a goal that you haven't even seen in the map yet in many cases. And then so down the bottom we compare 3 different models over this sort of fuller experiment. So the first is a hand-coded model where we just want to exploit the data set. So we work out how far it is on average to the goal, which is about 15 meters or something. We then look at the map the agent has built, and we look at the radius at that distance, and we choose the point that has the most observed parts of the map in the nearest neighbourhood around it, which is exploiting the fact that we're on average going towards the goal. And so if we've built up a map of that area and it's about 15 metres away, it could well be the goal. So that's the hand-coded solution. The second one is the LinguiNet only, which is the Cornell paper where we just try to do a global prediction of where the goal is. And the third is our filter at the moment, which is the sort of impoverished version that still doesn't have the heading, but hopefully, at least is showing promise. And so you can see that in terms of, I guess, overall success at predicting where the goal is within 3 metres, you can get around 23% with this exploitative sort of hand-coded thing. The LinguiNet global prediction does about 38%, and then we do about 46% success with this filter that there is sort of reasoning around all the trajectories as well. So we're kind of, I guess, excited enough to want to share this, and I suppose the higher level message is that it seems worthwhile to add some structure back into these models. Geometry is one. So one aspect of that here is that we're using a pinhole camera model to project and build this map because these are things that we know from computer vision. The second is incorporating algorithmic priors, and so using something like a differentiable Bayes filter as a component within this larger model seems to be quite an interesting way of trying to reason about where the goal actually is. And it sort of naturally then does what people have been doing with beam search in the actual environment to try to reason about the likelihood of competing trajectories, we can then do in a principled way in the map without having to physically move the robot. And so I hope you'll indulge me that this isn't the full result on the entire task yet, but that is going to follow fairly soon, I hope. So I'm sorry, I've kind of talked for much longer than I expected. I'll just say one more minute and then I'm going to be done. So in terms of, I guess, future work, which is something that's always of interest, has any of this work, got us to where we wanted to be in this motivation? And I think you'll agree we're not there yet. Two things only I'll just mention as things that are of interest to me. So one is personalising these sort of AI systems. There's this general approach where we're building an AI system, a vision and language system. We're going to sort of imagine the use cases. We're going to pay a bunch of people to collect some data, which is, all our data now is manufactured. We're going to train and validate a model, and then we're going to deploy this to a whole bunch of users. And so one sort of point about this is that most of the data that will be experienced by this system is seen after it's deployed. And so clearly there are ways that you can then capture some of that data and use it to improve the model. But I think there's to me at least, a bigger issue, and that is that when we actually deploy these systems, particularly if we're talking about systems that are situated in people's homes with particular users that will then be in a stable relationship for a long period of time, there isn't really one single target domain. And so there's this sort of problem that all of these users will be both heterogeneous but also stable in that these systems are likely to be used by one person in one place for a long period of time. And so to me, this seems like the wrong sort of approach to do this, deploy once and then release these things into the wild. I also don't think the sort of generic lifelong learning approaches are necessarily the best way to approach this problem, because in my opinion, I think we ought to be taking advantage of the user as a teacher explicitly in these scenarios, the same way that human children will not develop without very close attention from adults. We should also try to take advantage of the kind of teaching ability and interest of users. And so I'm kind of happy to say that, I think we should be aiming to put power in the hands of users, and that users will be smart and creative and sort of, highly motivated like they are in online games and, hacking devices and building game mods, etc., to improve these AI systems if we give them the tools to do so. So that's sort of one direction to me that is of, fairly significant interest. And we're sort of starting to look at scenarios where you could set this up. And some of the challenges here are things like having an agent that can understand natural language feedback, having an agent that can generate and represent its future intentions in order for humans to then provide that feedback. And there's a sort of a large-scale meta-learning problem here, which I think goes well beyond what is sort of currently investigated. So the final thing I'll just briefly mention is in terms of cooperative dialogue training. I think there's this trend that we've seen, data augmentation works really well in computer vision. Back translation works great in machine translation. In RL, we do self-play against other agents. But cooperative training of dialogue agents is still a really big problem. If we optimize in language space, we drift very far away from natural language. And so I at least think that in the case where we're talking about visually grounded systems, putting in algorithmic priors, for example, if you're generating visual instructions, perhaps we should be optimizing over the choice of visual landmarks that you refer to and not optimizing in the space of, the actual language words themselves. And so, these types of structural things, I think are, a solution I'm kind of interested to investigate further. So lots of people have been involved in this work, which I'd like to acknowledge. And I have talked way too long. I didn't realize it would be so long. I'm sorry. Yes.
Okay, we thank you.
Let me ask kind of one kind of very kind of I think about image understanding question. So in the first part you talk about image captioning. Essentially, it's trying to understand what's in the image. So the output is the caption, like human sentence, something like that. But we have some difficulty to evaluate whether kind of this caption is close to human caption or not, because as Sue said, we have variance in the human description. But another way to formulate the image understanding problem is we think that the output is just the objects, the attributes of the objects, the relation of the objects, and just so this is some objective output. It's not like caption. So do you think? So how do you compare these two ways to do image understanding?
So I think if you output something like a scene graph, so that is nice in the sense that it's much easier to evaluate. But yeah, I guess it's not necessarily going to get us all the way. We need to go towards systems that will provide this very natural interface with humans. The problem of evaluation of text and visually grounded text is going to keep us busy for a while, I think. Another way around it, I guess, is to evaluate on the task of interest rather than on the language itself, which is one of the nice things that we liked about the instruction following vision and language navigation task. So even now we're starting to actually work on the problem of generating those instructions, and we can evaluate that with a whole bunch of different agents that follow instructions and score them on, how well they go at reaching the goal. And so I guess if you can find a task to evaluate rather than on language, that can also be helpful. Probably not a very satisfying answer. All right. Thank you again. I really appreciate coming here. So.